Picking up where we left off last week, I want to talk about a few different calendar systems that we use, focusing mostly on the lunar, solar, and the lunisolar, and then start talking about the stellar calendars. Once we start talking about the stellar calendars, it's going to be around that time we jump into stellarium so we can actually see how this stuff works. And everybody who will be utilizing stellarium, which is pretty much everybody who's doing cultural and indigenous astronomy research, you're going to have to know this in some actual depth and detail. So in particular, Jack, Logan, Daunton, Jamie, Amanda, you guys specifically are going to really need this. Those of you who are doing more of the philosophical or sociological space futures type stuff, it won't be as important, but it's still good that everybody knows how it works. So lunar calendars obviously are based on the movements of the moon and how we can synchronize those into time. I think as most of us would be familiar, the duration of a lunar calendar over a certain number of lunations does not equal the same as the sun cycle. Therefore, we have to find ways of synchronizing them. But let's just start off with the lunar calendar. So we go through this based on lunar phases. There's actually two different types of calendars, lunar calendars we talk about. Before I even get into lunar phases, because this is really talking about one of them in particular, do we remember the difference between sidereal and synodic? A lot of people are saying, everybody raise your hand if you know the difference between sidereal and synodic. Good. I'm glad that everybody thinks they know everything about this. Doesn't. All right. What's the difference between them?
Sidereal is the time it takes for the moon to return to its position compared to the background stars. Synodic is the time it takes for the moon to return to its original phase.
Right. So this applies to any of these objects. Sidereal refers to its position relative to background stars, right? So there's the sidereal position of Venus, the synodic position of Venus. Any celestial object will have those two. So in terms of lunar phases, the duration of time it takes for the moon to go through a full set of phases and back around again is how long?
11 years?
No?
Roughly 28 days.
29.5 days, slightly off by the 0.5. It's about 29 and a half days, which is where the roughly 30-day calendar comes from, which means there's just over 12 lunations in a solar year of 365 and a quarter days. However, most people will say, oh, but a lunar calendar is 13 months. Where does that come from? Because the sidereal month is 27.3 days. It's a few days shorter. We're going to talk about why that's the case. So if you do that, the number is closer to 13. So it's important that we understand how these things work. So when we go to lunar phases, they're obviously going to be switched, whether you're looking at them from the northern and southern hemisphere. But we're going to start off with the new moon is when the moon is between the Earth and the sun. The lit side of the moon is the side facing away from us. So for approximately 3 days, we are unable to see the moon simply because we're looking at the dark side of it, literally. As the moon begins to move around, because remember, the moon is the only object that is continually in retrograde. The moon starts to move around us, and as it does, we start to see that lit side as a very thin crescent. That is actually what the new moon originally meant, of course. The moon disappears, and it's the new moon coming back. And each night, we're going to see more and more of the lit side of the moon. When we begin to see more of the moon lit up overnight, we call that waxing, up until it reaches first quarter. So first quarter is exactly when half the moon is lit. From our perspective, it'll be the left half of the moon. From the northern hemisphere perspective, it'll be the right half of the moon. Once more than half of the moon is lit up, we start calling it gibbous. So it's waxing crescent for that first week, then waxing gibbous for the second week, until the moon moves around to where it's in opposition from the sun. When it's in opposition from the sun, it rises as the sun sets. That therefore we are seeing, from our perspective, the entire half of the moon is lit up for us, so it looks full. And then as it begins to wane, so between full moon and new moon, As we see less of the lit side, we call it waning. It begins going through waning gibbous until the moon gradually fades away, until the opposite half of the moon is lit up from our perspective, the right half from the southern hemisphere, the north half of the northern hemisphere. So we get into here, it's about first quarter, goes around to full, starts moving on to about third quarter here, and then gradually fades away through waning crescent until it appears a very thin crescent, then disappears and goes away for 3 days. So here's the main general phases of how they're going to look in opposition, whether it's the northern or the southern hemisphere. Now, of course, with this, it's not just what the moon looks like, because we cannot separate space and time. They're always connected. It's also when the moon is going to rise or set throughout the day. So if we are in a new moon, when there's alignment between the earth, moon, and the sun, what time of the day is the new moon going to rise? I want everybody else to answer, not you. When is the new moon going to rise? What time of day?
Sunrise? Okay.
I get sunrise, I get midday.
And I said sunset?
The new moon means it's right next to the sun in the sky. Therefore, if the sun rises, that's where the moon's going to rise, and it's going to set when the moon sets. So the new moon is right with the sun in the sky, right? Now, as time goes on, it's going to rise a little bit further each day. At first quarter, when there's 90 degrees between the sun, the earth, and the moon, when is the moon going to rise at first quarter? Anybody else? The philosophers, historians, educators? Say it out loud. 1, 2, 3.
Midday.
Midday, thank you. Midday, right? Now, when it's full moon, when is the moon going to rise?
Sunset.
Sunset. It's easy. If it rises when it's new moon, if it's with the sun, it's going to rise at sunset. If it's full moon, it's rising, or if it's rising at sunrise and then it rises at sunset, halfway through is going to be first quarter. So it's waxing or it's waning away when it's third quarter, or sometimes called last quarter moon. What time of the day is it going to rise? 1, 2, 3.
Midnight.
Midnight. Very good. Excellent. And then continues moving around again. So that's the idea of a lunation. That is the synodic period of the moon, 29.5, roughly approximated. There's a tiny fraction off there, but 29.5 days, right? Now, of course, indigenous culture.
Which was the 27.5 and which was the 29.5?
Okay, so sidereal is 27.3. We're going to talk about that in a second, don't worry. Synodic is a 29.5.
Gotcha.
Now, lots of different cultures around the world are going to have their own names for the moon. They're going to have their own cultural meanings and interpretations about that. But what I want to do is jump into the Hawaiian moon phases. So when we talk about the 4 major phases are new moon, first quarter, full moon, third quarter. All right, those are the major ones. And the periods between them are waxing crescent, waxing gibbous, waning crescent. But those are just the major points of it, or the phases between them, or the periods between them. In a lot of Polynesian cultures, there's a distinct name for every single day of lunations. When you look at the moon, you wouldn't say it's waxing crescent, you'd say it's kulua for that particular day, depending on how much of the moon is illuminated. So they're grouped into 3 sets, and you can see them up here. I can send you some details about, if you want to go more deeply into what they all made and how they work, it's kind of cool. The video here, which I'm just going to play a second of, is sort of a kid's hand game. You're clapping and singing as you go along, is a mnemonic for how you would learn these. What I love to do in one of my classes, and I may do this in archaeoastronomy next semester, keep that in mind, is have the students memorize the 30 days of lunation in the Hawaiian calendar. I'm just going to play this real quick, see how I feel for it. Oh, wait. No, we're not gonna do that, sorry. That's gonna cause the audio here to screw up because we're having to do this weird thing. Anyway, I'll put the video online, you can see it there. Now, of course, one of the aspects about the lunation and the reason that the lunar calendars are so important is they tie into tides. I think it's important to understand how the tides actually work. So there are going to be the two major factors with the tides are the gravity between the Earth and the Sun and the gravity between the Earth and the Moon. So the tides are primarily caused by the Moon pulling against the Earth because the oceans of water, they're fluid, they're going to bulge towards the Moon, but because of conservation of momentum and energy principles, there's going to be a counterbalancing bulge on the exact opposite side of the Earth. So wherever the Moon is directly above is when we're going to have the high tide. It actually drags a little bit. It's not exactly when it's above. It's a little bit later. It drags as we go through because of the inertia of the oceans. But that's the fundamental sort of preschool version of how that works. Now, when we have the gravity of the Sun and the Moon in direct alignment, then it's going to be higher than normal. That's when we're going to have our spring tides. So we can get the spring tide during a new moon. We can also get a spring tide during a full moon. Because of the angular conservation principles, that bulge on the opposite side of the Earth is going to be higher or lower when you have that related gravity from the Earth and from the Moon and the Sun anyway. As we're going to see in a graph, the spring tides, even though they're higher than normal, are not equal to each other. You actually get more, the highest tides is when they're a new moon. But when we talk about high tides, it means we get the highest tide and the lowest tide. It means the amplitude between the wave of the high and low tide is the greatest. Now, they're going to be minimal at the first and third quarter moons, when the gravitational pull of the moon is kind of counteracting that of the sun because they're working in opposition to each other. That's when we get the neap tides. And again, the neap tides are going to have the lowest amplitude. It's the difference between high and low tide is going to be the lowest. So some people confuse that, thinking that high tides means the water is always super high, but no, it gets the highest, but it also gets the lowest. It's the change in amplitude. So here you can actually look at this. You can see the difference. So this is something I did during my PhD. I looked at the amplitudes of them relative to the time periods for the lunar phases. I forget exactly where it was from, somewhere coastal Northern Territory. It doesn't really matter. So what you can see is you do get these spring tides of full and new moon, but they're not equal to each other. The new moon is when you have that combined gravity of the sun and the moon in the same direction. You're going to have the high, yes.
Just so apogee and perigee, of course, play into this.
We're going to get there in a minute.
Yeah, just do eclipses also play into this?
What do you mean?
Like when an eclipse occurs, if that is at a point of high or low tide, does that cause a similar? Of course, it would be
Technically, it would, but it's probably going to be negligible compared to the moon being off the sun by half a degree or something like that.
Yeah. Okay. Yeah.
I mean, there would be, yes.
Yeah.
If you're in the middle of the pathway of a solar eclipse, then yes, probably going to have an impact. But when you think about the difference in the gravitational pull and that direct alignment, and you think about the dragging effect, it's not going to be that noticeable. You're not going to be
it's negligible.
An eclipse and see something happen. It's going to be really noticeable now.
Yeah, gotcha. Sorry.
Nope, good. But what I'm getting at here is the change in amplitude isn't that difference, but the measurement of high and low tide, where the high tide is, clearly is. So if this is 2 meters, 2.5 meters, we can say it's about 2.5 meters here, but up here, it's almost slightly above 2.5 meters. But if you look at the actual amplitude between high and low tide, it is greater during a new moon. But that's kind of the idea. And the first quarter and the last quarter kind of work in similar ways. It's just something to have in mind. There's all kinds of gory detail when it comes to this. And what I did mention last time, and you just brought up, which I think is important to mention, we get perigee and apogee, and we get perihelion and aphelion. both of those factors are going to impact the height of tides, the elevation of tides. So if the moon is at perigee, where it's closer to us, during a new moon, we're going to have higher normal tides. And when it's at apogee, they're going to be lower than normal high tides. If it happens to be when that occurs during new moon or full moon. We also have to look at where the Earth goes around the sun. So if we're at perihelion, when the Earth is closest to the sun, then that's going to have a higher gravitational effect, which means we're going to have higher than normal. Now, the creme de la creme worst position we can imagine is when everything lines up. So we're in a perigee, new moon, when the Earth is at perihelion. That would be bad. That would be catastrophically bad.
How often does that happen?
It's a good question. I don't know. I'm sure we can look it up.
Be a good day for surfing.
Because sometimes we might be at perihelion with the sun, but the moon is at perigee when it's first quarter or something, where it's not, there's going to be the gravitational effects moving it's closer, but the moon's going to be kind of countering that a little bit. But that's the worst case scenario. And that's definitely not something we want. And coincidentally, in a script that I'm writing for an IMAX show, part of the narrative is this young boy, Islander boy named Matt, realizes that this is going to happen. It's going to be a perigee moon happening when they're the closest. I'm not going to say all this in the film, but this is the idea behind it, right? And that's going to cause massive flooding in the community, which in places in the Torres Strait, which are a lot of the islands are very low lying, and in other parts of the Pacific, this is catastrophic, and this does happen sometimes.
Really, because I'm a big speculator at the moment, because basically growing up on the North Sea shoreline or close to that, the wind conditions were far more important. I mean, spring tide and definitely makes a difference, but the variation of spring tide compared to if you have a northwester blowing in constantly, then the spring tide becomes catastrophic, not because the celestial alignments in that case. This is very different in the Pacific.
Yeah, it is a bit. So there are parts of WA, for example, where the amplitude and tide is over 10 meters.
Yeah.
So it's going to be depending on what
geography has 950, so it's also very similar to that.
Yeah.
But because basically if the wind blows in, then the tide just stays, and that's the problem. So it's but might be a different thing if it's not a bay side.
There have been problems in the past in the Torres Strait and Pacific Islands. There's been mass floodings during the king tide when the Earth is at perihelion, and that alone has caused massive flooding in some of the islands where it's almost taken an entire island underwater. If you have the added effect, we're at a new moon and not only a new moon when we're at perihelion, but if it's a perigee new moon, then it's going to be even worse. That tends to occur around the transition. Actually, in the Torres Strait around the equator, it tends to occur during the onset of the monsoon season because it's about 2 weeks after the summer solstice here that we get the point where it's perihelion, which is just right into kicking off the monsoon season, which kind of kicks off end of October or end of November, but really kicks off around the solstice. So that's dominated by northwesterly trade winds. I didn't want to get too much into that part. I just want to give an idea about how we go about figuring out lunar calendars and how lunation works, because most of the calendars that we tend to use tend to be based on them being 29 to 30 days, which is a big approximation to the solar calendar, as we're going to talk about, but not exactly. So in a lot of cultures around the world, especially the Islamic calendars, that one's a purely lunar calendar with 12 months, each month being either 29 to 30 days, which usually kicks off with the first sighting of the lunar crescent by human eye after a new moon. So in that case, it's literally the new moon, the traditional sense. You see that very first crescent, which depending on the conditions and weather and your eyes, you could see up to a day after the actual physical scientific definition of a new moon, but it's very slim, usually about a day and a half later. See that. So the Chinese calendar is an example of a solely lunar. We combine those 12 years, or we combine these cycles. So we've got our solar calendar, which is 365 and a quarter days. which we mostly mark out from solstice to solstice. We have that tiny bit being over each year means every 4 years it adds up to an extra day. So we have that intercalacial correction within that, being that extra day. I mean, you're trying to do lunar calendars and you're trying to synchronize them, you're going to have something similar. You're going to have intercalary month every 2 or 3 years where you put things in there. So you're going to have these things you have to use to synchronize. So a lunar calendar is a calendar based on the monthly cycles of the moon's phases, which are the synodic months, which are lunations. That's purely about the phases. In contrast to solar calendars, whose annual cycles are based only directly on the solar year. The Gregorian calendar is a solar calendar system that originally evolved out of a lunar calendar system. And the purely lunar calendar is also distinguished from a lunisolar calendar, because the lunar months are brought into alignment with the solar year through some process of intercalation.
I mean, which of the ancient, and I'll use that word, whatever, cultures has the most accurate determination?
Well, it depends on the context of what you're trying to look for. Right. So I think most cultures would have started off with basic lunar calendars because that's the shortest cycle. But over the course of a year, because you've got lunar calendars, solar calendars, lunisolar calendars, but mostly what tend to be used here, we're going to talk about stellarium or the stellar calendars, which mark the position of the stars back each year, which roughly coincides with the solar calendar. But those are the ones that are shifted by precession over time, where precession doesn't impact the solar positions, nutation and the obliquity of the Earth's orbit impacts that. And that changes over, relatively short time, but the maximum variation of that occurs about every 41,000 years by a couple of degrees. Whereas the process of precession equinoxes changes by 1 degree every 72 years along the ecliptic. So it's much more significant when you're looking over longer periods of time. This becomes an interesting question because there were cultures who had developed super precise calendars and trying to find ways of figuring out how they're going to work. But there were some cultures like the Mersey who scholars would say their seasonal calendars were very rudimentary and their use of lunar and solar were very inaccurate. But they had other stellar ways of utilizing it that was very focused on the local geography, particularly those along the Omo River who would use flood retreat agriculture, because it timed in with the setting of the stars and the Southern Cross and the pointers, because they worked out the angular distance between them and their timing exactly worked out with the pulsations of the Omo River. So when you're doing flood retreat agriculture, you've got to be able to plant along the riverbank so the flooding will water them. But if you do it too early, it's going to flood it away. If you do it too late, it's going to dry up. You have to get it exactly right, but you have to get the timing down. Because there were multiple pulsations in the river, depending on seasonal rainfall further upstream near Lake Victoria. The same thing that would cause a flooding of the Nile. So within that, they had to predict exactly what was going to occur. And they utilized stars and the Southern Cross and the pointers that exactly corresponded to that. And the mnemonic for that was to name the stars after the terrestrial aspects of that, which is pretty cool. Okay, so lunar month is the time between 2 successive syzygies, and I'm using syzygy in a general sense as the alignment between 3 bodies. This is when the Earth, Moon, and the Sun are in alignment. When they're exactly in precise alignment, given their geographic centers, that's where we're going to wind up getting things like eclipses. But the general alignment of them is what we can think of as a syzygy, which syzygy is an awesome Scrabble word. If you can use it, S-Y-Z-Y-G-Y.
I was going to say the exact same thing.
You got to use a couple of those blank tiles, I think, to get the Y's in there. So here's a little math problem for everybody. It's a very simple one. So we're going to look at your age in Islamic lunar years. So everybody get a pen and paper out if you don't have one already. Multiply the number of years you've been alive by 365 days. Add an extra day for each year, divisible by 4. Now, it's not the same as just taking your age and multiplying it by 365 and a quarter days. The number of years you've been alive by 365 plus an extra day for each year that's divisible by 4. It's not a partial year, but a whole year.
So when you say multiply the number of
Didn't you
years,
take this class already?
I did, and I got this wrong the first time as well, so I want to double check. So the number of years you've been alive by 365.
Yes.
Yeah, okay.
And then for every whole 4 years that you've been alive, you add an extra day. Which means it wouldn't be this year. Unless it happened to be, unless your birthday was in the end of the year.
Yeah.
But we're not here on the 31st of December anyway. Add up the days since your last birthday and add that to the result in step number 2. Divide the total by 29.53. So we say 29.5 is actually 29.53. Slight variations in that. Nothing in astronomy is simple. Nothing orbits in perfect circles. So everything we do, if you start digging into it, it's going to be more complicated than it looks before, right? We're just using approximations right now for simplicity. Divide by 13. Truncate the decimal places, and that is your age in lunar years. So, what's your age in lunar years, everybody? We'll start in the back of the class. Who's going to go first? Now we're going to start over here. Gerard, how old are you in lunar years?
56,
56 lunar years. And what's your actual age?
59.
I did something very wrong. I've got 969.
That's very Moses. That's very difficult. Years. I think you forgot. Did you forget a step? By dividing, I think.
Dividing by 13.
Yes.
All right. We'll come back to you. Jack, what'd you get?
19.69.
What's your actual age?
20.
The older you are, the greater the gap between your lunar and your solar age. The younger you are, the closer they're together. Yep, Asha?
I was still writing down the instructions, but I do have my answer from second semester last year.
No cheating, come on. What'd you have?
But you've aged since.
It was 27. I am 28.
Yeah, it's gonna be different now, right?
Yeah, well, slightly. I was, 27 at 28, actually. I turned 29 soon, so I'm assuming I might be even 28 now.
All right. Sam, what do you got?
I'm 15, but my wife would say that's my level of maturity. So way out.
I'd say way out.
Way out.
Let's try this again.
I'll do it again.
Take your age times 365. For every 4 years you have to add a leap year, but it can't be the last one you've just done. For every year, let's look at this. For each year divisible by 4. So if that can be divisible by 4, then you add that extra day in. Add the day since your last birthday. Add that to that result. Sorry, my steps in step 2 and 3 are off, but you know what I mean. This should say in step 1, this should say in step 2. You get the idea.
60. Is that closer?
Yeah.
What's your actual age?
64.
Yeah, there we go. That's close. Definitely much better. All right, Morgan, what'd you get?
I'm trying to install Stellarium and it's not working. It keeps.
Don't cheat.
I'm cheating.
I'm not gonna get any. What's your lunar age?
I don't know. I didn't do it.
Oh,
I'm literally trying to get Stellarium.
There's always one of
Always
those ones, yeah.
Varying Dwayne.
64,
I know.
what's your actual age?
66. But this is cool because I'm going to be have a birthday in minutes.
So that's 2 years off.
That's
Yours was 3 years off.
Yeah, but mine's
because I did-
64 and 0.98 if you add the.
Okay.
So I'm about to have a birthday any minute now.
Yeah, but you can actually do a shortcut. You just cut 5% of your age.
Everybody's got to cheat.
No, sorry. This is just putting all those steps into one.
It's approximation. Yeah, 5% of your age.
No, it's not an abstract. Oh, okay. It's
Not in abstract.
it's
It's
5.103% of that. That's the
5.103. Yeah. What'd you get, Dom?
27.
Yeah, what?
I got 27.
Your age is? Yeah.
35.8. I'm 37.
Okay, good, excellent. Okay, so moving on,
Dwayne, your
Shut up.
age.
I'm too busy dealing with the class to do it. So let's talk about this is the important part. So sidereal month versus a synodic month. Sidereal month, the period of the moon's orbit with respect to the celestial sphere of, I say, apparently fixed stars, right? Because we know those change over long periods of time, but for shorter time scales, very fine approximation. The time it takes the moon to return to the similar position among the stars. Now, we do know something about the moon. For those of you who, I don't have a marker in here, do I? I'll show this on stellarium, which we're going to get into in a minute. We have the ecliptic in the sky, the path of the sun, right? The moon moves either side of the ecliptic over a month, right? So even during a month, it's not always going to come back to the exact same spot in the sky. It takes 18 point something years for that to happen. But it's going to be the same relative spot in the sky relative to the background stars. So the duration of that, 27 days, 7 hours, 43 minutes, 11.6 seconds, or just slightly over 27.3 days. As opposed to a synodic month, this is going through full lunation. This is the full range of lunar phases. It's 2.2 days longer than a sidereal month, which is 29.531 days, so slightly over that. Why is that the case? Because the Earth is orbiting the sun. That's why they're not exactly the same. So if you look here, when the moon comes back around relative to where the sun is, it takes an extra couple of days to go back to that position because we're going around. So we've got our position there, day 0, starting off from when they're in this perfect syzygy. As they go around, when it comes back to the same direction with the background star, so the sun here is pointing to star X. We come back, the time it takes to go to star X, that's the sidereal, but because we've gone around the sun, the angle between the Earth and the sun has changed. To account for that extra angle is the extra 2.2 days. So when you take that over the course of 12 months, that's why some will say a lunar month is just over 12 months, and some will say, no, it's 13 months. Well, it depends on how you're going to utilize it. You're talking about your sidereal or your synodic. People asking questions, I've been ignoring them.
I'm still 27.
So Amanda says that lots of Near Eastern cultures had at least 2 calendars, one cultic and one civil. Egypt had both solar and lunisolar calendars, and they synchronized the 2 calendars together. Awesome. Yeah, this is... Amanda gives a guest lecture in archaeoastronomy.
It's very good.
I have never seen it.
You should come.
I should.
It's your subject.
It's my subject, but you teach the second half of it.
Wait, so she could be saying whatever she like, complete nonsense in that lecture, and you would have no idea.
You've definitely met Amanda.
Wasn't that what happened to?
I would have no idea. No, I wouldn't. There's a certain level of trust that we have here, but I also, grilling you guys on these questions also helps. Mohammed Daniel is saying, sorry, I forgot to mention earlier, he's from one of the lunar sighting committee right now in Malaysia. The mandatory observation is only for 3 months out of the 12. The rest is optional. So people say, all right, cool.
Dwayne, really quickly whilst we're on the break, going back to that presentation that we were in, I sent a question on the destructive nature of it, and my graduate was still in the meeting after we left. They got back to us. If they're actually looking at a stone arrangement, they come out to the site, they put a blacked out tent around the sample, they take it out from the bottom, core the underside, then reposition it exactly as it was.
Right.
So there's no obvious destruction to the top, everything's...
But it does require moving it, right? But you don't have
It
to
require moving, but they come out, they tent it out, they do it only with written permission of the traditional owners and only with the TOs there. So it is potentially still possible.
Awesome, that's good to hear. Yeah. Perfect. Well, that's a little, well, let's watch this because I've been talking about it, but let's just get a little video. Let's see how this goes. Come on. I'm not even sure if it's showing. Can everybody online even see that?
No.
I can't see other people online. Can those of you online see this video? They can? Good. There's no sound. You don't need sound. Yeah, we didn't talk about draconic months and mythological months. We didn't talk about tropical months. We're just keeping it simple in here for now.
Is it supposed to be
You're
playing?
supposed to see something?
You're still doing it.
Oh, always somebody can see something. It's always something. It's always something.
Just wondering what I was missing. It's in real time.
All right, well, the people online can see, you guys can't, just never mind. Just never, I'm not gonna. Yeah, I don't know. It's always,
We'll watch the recording.
Zoom never works the way you want it to. It came up on my computer screen, but I'm not sharing this, anyway. Whatever. Look, I wanna step away from this right now. We can talk about Gregorian months and lunar marks on bones, and these are probably some of the earliest calendars ever utilized were lunar months and marks on things about that, but I don't wanna get too much into that right now. What I wanna do is go back to stellarium. So I'm gonna stop sharing with everybody for a second. So I can pull up stellarium and we can have a bit of a detailed look at this, but I'm gonna give everybody a 5-minute break before we do that.
Try to open it again.
It does all this stuff automatically. I can't tell if people can see it or they can't see it. I don't know what's going on. We're gonna take 5 minutes, guys. Come back in 5 minutes. 3:07, we're coming back at 3:13.
You good, bro? Oh, fine.
No, you can't download this. It's all good.
The restaurant.
Yeah.
Are they shutting down?
Shutting down the catering side.
Oh, okay.
Is anybody on this Zoom now? Are you on the Zoom?
I've left.
Somebody jump. I can't see everybody. Can you guys see stellarium on the computer? You can see stellarium? Okay, we're all good.
Okay, good.
You're a champion of the people.
I
swear.
two clicks. You would have figured it out.
I don't know that I would have. I've tried a few times, given up. Thank you.
It's always the simplest solutions.
Now, how do I import that into Stellarium?
Oh, that's a great question. No idea.
Okay.
Oh, okay.
Should be under configuration.
Jeez. 6 weeks ago, 4 weeks ago.
Oh,
God.
Oh wait, it's Horizon does?
This is why I'm
You
terrified.
can let
of
me
college.
back in. I can monitor questions and things on the Zoom for you.
yeah.
All right.
John.
So what's the actual
How have you been, Tom?
It's
How are you?
Yeah, well, thanks.
Yeah.
I was really drunk the last time we spoke. We only had a catch up on this app. Was that last night at the house? I ended up leaving that night.
The actual location window.
It's wonderful.
I'm trying to remember how.
Or I'm sitting.
Especially on 2 hour break right back.
Oh, yeah, I know, I just switched off and I actually tried to watch a
It's only
Netflix
the 40th
series,
of
Le Parent,
November.
which is fantastic, but it's all in French. And I completely lost it within like the first half an hour.
It'd be good to let it know, maybe.
And Duane, you have your hand up. Do you have a question?
It's driving, right?
If you do anything, all it says, oh, you have a hand raised.
Yeah, okay.
This is why I'm terrified of the conference and having an online option, because nothing ever goes the way you want it to. Everything is gonna go bad. But Amanda's, not Amanda, Jesus. Sorry. Bridget called me earlier today and has another company who's gonna give us pricing, who may be able to handle all of that
Wonderful.
for what may just be a few $1,000s.
Yeah.
And hopefully if I can get the Australian Space Agency to chip in their fund, that will cover that. Because at the moment, the incoming and outgoing for the conference is within $200. The tens and tens of thousands of dollars of money coming in, going out, when it's all filtered through how we're budgeting everything to make it not-for-profit, I've got, right now, we are at a $227 surplus.
That's either really lucky or really, really well planned on your part.
Let's go with the latter.
For the lanyards then, how you doing?
I found a company that does lanyards, that'll do custom lanyards for as little as $2.50 each. That includes bit, and I'll probably get it with the orange color of Isaac. This is International Astronomical Society for blah, blah, blah around the edge of it. Otherwise, if it's double that, it's gonna be too much money.
Okay,
But it's an option. I still wanna keep looking at that. That's not set.
Mm-hmm.
Early bird ended yesterday.
How much was it you could get those for, Trevor?
I got one guy saying $4, and the other one, another person came online and said 5. So it's between 4 and 5. If you
If we could get the lanyard and the plastic thing it comes in together, if we can get that for $4, then it might be possible.
Sure. Yeah. Well, you got my email?
I hope that I do.
The other guy's email. If you just email him, get in touch, and he'll send the quote to you. Okay. So.
All right. Wait, sounds good. We'll get there. We'll figure it out. Yep. Oh, and Dan, sorry to hear about the situation. I think it's pretty unsurprising given the circumstances in the US at the moment. But
thanks, Duane. Yeah, I mean, pretty upset about it earlier this week, but also really excited that we got to, build this idea further and all the other stuff that we're working on in between. And who knows, I might have never joined this group or had the plans to come to the conference this summer if it wasn't for the process that we went through for it. So
it can lead to very positive outcomes in a different way you didn't expect. So that's really good.
Yeah. I got to ask you real quick, we're on break and while we're talking, is it Zugabu Mabag? Is that correct?
Zugabao.
Mabag. Okay, because I'm recording the vocals to that song this weekend, and I want to make sure I actually sing that correctly.
Zugabao, someone say Zugabal, Bao, it's, if you probably hear somebody saying that in Catalan, go, yeah, none of them will be able to pronounce it. But Zugabal Mabag is very close. That's good enough.
Zugabal Mabag.
Zugabal Mabag.
Mabag. Okay. I'll be the first person ever to put that into a pop song.
It'll be awesome. Yeah, I mean, I don't know if you mind others knowing that just your thing got knocked back because of Trump.
Oh, that's cool, actually, because
it's a bit ridiculous, but it's not terribly surprising.
I sort of tell it what you want, but if you do, that's fine.
Oh, yeah.
Okay, what time is it?
do you want sidereal time, lunar time?
3:13.
Virginia, get on to right. Okay, so everybody can see stellarium up in the window, right, from the screen. I'm trying to get all this stuff out of the way, so there's not too much, so much crowding and zooming everything all. Wait, actually, you guys are fine here. This is good enough. So stellarium is an incredibly powerful planetarium software that you can utilize on your laptop, your device, phones, that can tell you exactly what's in the sky at any time, now, from any location, including any of the planets in our solar system, and see exactly what would be in the sky, where it would look like, and where it would be. So I want to lead everybody through this process and show you what all these buttons on the bottom mean, what all the buttons over here mean, and how we're going to utilize this. When everybody in the class is done chatting amongst themselves. So if you look down here in the bottom corner, you're going to see it says Earth. Well, actually it says Duane Hamacher screen. It's always something in the way, I swear. It'll say Earth, this is the planet we're looking from, obviously, but stellarium allows you to look at things from Mars or from the moon as well. And it has the coordinates and latitude and longitude where you are. And over here, it shows you the date, the time zone, all these details. So what I want to do is just start off, before we go into things on the side, I just want to start off at the bottom. What is all this stuff telling you? This is the power button. If you click that, it's going to take down everything. Don't touch that until you're done. These are play, which you can click and that will pause it, which is really useful when you're trying to work on things. And if it's playing in real time, everything's moving around. The more you zoom into something, the faster it's moving. So you click that and that stops it. These simply fast forward, rewind. This button here will display satellites. I would highly recommend anything you're doing to get rid of that because you don't need that. This is going to be coordinate system stuff you don't need to worry about right now. There's a few things I wouldn't mess with worrying about. These buttons I wouldn't worry about right now.
Navigational stars on the right.
Yeah,
So
that
just,
right.
just points down then. Points down.
So navigational stars, I haven't seen that one before. That's something relatively new that's popped up in the edition that I've got.
A couple of years ago, yeah, but it wasn't there for a long time. It hasn't been on very long.
This one here, this is meteor showers. Wouldn't worry too much about that one. Now, this is a really good one. This is archaeolines. And this one is going to bring in your solstices, your equinox, and your lunar major and minor standstills.
Real quick, Duane. Archaeolines, you need to have a plugin installed. It doesn't come default with people who've just freshly installed Stellarium.
Okay, good point. I'm going to show this as I have it, and then we'll talk about how you can upload the different plugins within it. But archaeolines will be a symbol that if it's not already uploaded, we'll show you how to upload that. It shows a trilithon from Stonehenge with the sun-like thing in the middle of it. That's a symbol. This here is a really useful one. This measures angles between things. So I can hold it down and then measure an angle between two different objects. So I can do, like down here, you can see how it works. Going long distances. And of course, that's measuring the angular distance between objects in the celestial sphere. This button simply does the screen in or screen out. This one here is if you're going to be outside, you can actually plug your telescope into Stellarium and have it synchronized. You can have your telescope point wherever you want. But if you're outside doing any kind of stargazing, you do not want white light. So clicking this just simply gives you the red light, which is okay. This one is really awesome. It's a centering thing. I feel like I need to show some stars because right now it's defaulted at this time of the day. So what I'm going to do is I'm going to go forward, and we're going to talk about this one later. I'm going to go forward tonight. So before I had this, if I want to see the angular distance between two celestial objects, I can go between Arcturus and the moon, which tonight would be, 78 degrees, quite far across the sky, but you get an idea of how that works. It's so annoying. This button has a telescope thing on it. Unless you're using it for your telescope, don't mess with it. That's what synchronizes them. This button here displays the planets, which is going to include asteroids and things of that nature. So I'm just going to pull this back so it shows the whole sky in the image. So if I click on this one, it'll show the planets or take them off. There aren't many up in the sky right now. This looks like a galaxy. Does exactly what you imagine it's going to do. It's going to show you all the background, deep sky objects, all the star clusters, nebula, all that kind of stuff, which can be very useful for what you're doing depending on what you're looking at. Don't pay attention to what I'm doing right now. I've got to change something real quick because I think not much was coming up. I'll talk about that in a minute. This that shows the stars, exactly what it's going to look like. You click on that, that takes the stars out. I'm sorry, this is the cardinal directions. Sorry. This is your north, south, east, west, cardinal points. I highly recommend leaving those on as a default. They're very good markers no matter what you're doing in here. These two are really important. This is your atmosphere. So if I take the atmosphere off, it's going to show you what things would look like if we were on the moon or something, right? The one next to it shows what looks like a hill with two trees. This is your land. Click that, it gets rid of the land.
Sorry, does that just show what magnitude of stars does that show? And can you change it?
Yeah.
Because I'm thinking about with Indigenous groups, the stars, the images, the construction of the stars in the sky is the same, but their interpretation of the relationship to create different pictures is different. So what level of magnitude would you recommend if you're talking about, for instance, Australian Indigenous astronomy or Tahitian astronomy, that sort of thing?
Well, given that Uncle Bill Idundamaharni, the last living fully initiated senior-old of the Waterman people, who's 94 years old, knows over 2,500 star names, I'd say you get under visibility, which is around 6 to 6.5 magnitude. I just
That would make a big difference. So it just makes a big difference in terms of explaining.
Yeah, I just pulled this up because it was at the moment when I was showing things, the atmosphere wasn't hardly showing anything. I'm just trying to do this for visual representation. But yeah, so when we get to star limitations, it's more the visibility magnitude limit you need to set for that.
That will work with someone.
So getting back to this, so this is the land and the sky. Over here are your two different coordinate systems, and it'll show in the little word right above it. This is your azimuthal grid and your equatorial grid. Your azimuthal grid sets up where they're all converging at the central point above our heads, which is zenith. So this shows the altitude of an object in the sky from 0 at the horizon to zenith at 90 degrees. And this shows the azimuth as it goes around, starting 0 at north and moving around to 90, 188 south, 278 west, and back around again. This will be extremely useful when we're doing seasonal calendar star work. Pull it up and zoom in. So sort of like what it look like from our perspective more realistically. So you get an idea of what this does. You can zoom in quite deeply to this. You can zoom in out so you see the whole sky in your image. But that's what the azimuthal grid does. And of course, when we're doing stellar calendars, it's useful to not have your ground because you want to be able to measure the altitude of the sun as well. We'll talk about that a bit more in a minute. I just want to lead everybody through what this does. If that's your azimuthal grid, the one next to it is your equatorial grid. And this, instead of going from zenith to nadir to the horizon, this goes from north to south celestial pole, with the celestial equator being what marks it off in the sky. So this point down here, this is the south celestial pole, which obviously being down where we are in Melbourne, you're not going to see the north celestial pole because it's well below the horizon. If you want to see where it is, you turn the land off, you can see it's way down here. You can see on there, if I click on that, if I click on the name of a star, it shows the star and all the detail on the left side of it. The color of the text represents the color of the star, in case you didn't know that. If I want to center that, I go back down to the centering button. I can just zoom into it. And we can see here the star Polaris. And we wonder, well, how far is Polaris actually away from the north celestial pole? Let's go back down to there's two ways you can do that, but I'm going to do this way just to show you how it works. Click on Polaris, then we drag that across. As you can see, so 37 arc minutes is about half a degree. So it's not 37 degrees, it's degrees in arc minutes and arc seconds. 60 arc minutes in an hour, so it's just over half a degree. But that gives you an approximation. So over here on the left, you're going to see lots of details about each star. You can look at the type of star. Is it a double star? Is it a variable star? It tells you its magnitude, its absolute magnitude. So it's a magnitude and its apparent magnitude are different, right? There's an absolute magnitude, which has a definition in astrophysics, where I believe it's the magnitude of a star, is it 1 light year or 1 parsec?
I think it's 1 parsec.
Yeah, it's the magnitude of a star, 1 parsec in space with nothing between you and the star, like no atmosphere or anything. That's how bright it would be. But of course, stars can be much further than a parsec away. They can be much closer, but our atmosphere is going to impact it. So as we look in the sky, we can see this star, Polaris, is magnitude 1.95. Now, Something that's important to recognize when you're using stellarium is that a star's apparent magnitude is going to change depending on its altitude in the sky. The closer it is towards zenith, the closer it's going to be to its true apparent magnitude. But the further down you get away from its highest point in the sky, it's going to the light's going to have to travel through a thicker level of the Earth's atmosphere, which more of the light is going to be extinct. It's going to be reflected and refracted and absorbed and things of that nature. It's going to give less accurate. Which means as you start to get down towards the horizon, there's going to be a point where the star basically disappears. That's going to be causing extinction. As we're going to talk about in a little bit, when we start looking at seasonal calendars in terms of stars, we generally set a limit of 5 degrees above the horizon as being the minimum limit you can use. That's going to depend on magnitude and other observing conditions, but it's a good first order approximation. So let's just give you an example of how that might look. So, hang on. Don't need that. I mean, it's below the horizon for us here. Well, let's not worry about that right now. Let's go back and look at the star Arcturus. Arcturus, its magnitude is 0.15. It's one of the first magnitude stars. So you can get all those details from the object, you can get details from Mars, but when you're looking at these objects again, there's a lot of information here. A lot of that you're not necessarily going to need, but this is going to give you the right ascension and declination in terms of the J2000. So every year, every 50 years, everything in the sky is mapped and given a very precise set of coordinates. Over time, because of stellar proper motion, the stars are going to shift a little bit. That's what you're going to get when you put the right ascension and declination on the date. It's going to tell you approximately what that's going to look like on the actual date you're observing. Because right now we're 25 years later. We're halfway between now and the next J2050 date. That's why these two numbers will be very close, but not exactly the same. You're going to get things here like your azimuth and your altitude. This is going to be your altaz system. This is going to tell you where it is in terms of the azimuth, 41.5 degrees, versus your altitude at almost 21.5 degrees up in the sky. This is your galactic and supergalactic longitude and latitude. I wouldn't worry about these. In fact, I'll show you where in the system you can get rid of all that stuff if you don't want it or need it. Your ecliptic longitude and latitude. There's a lot of stuff here. I'd probably say all of these you don't need to worry about. The ecliptic obliquity you don't need to worry about. What I would get down to is it tells you what the constellation that your star is in. It tells you its distance in light years. Its proper motion is how much the star moves over time in terms of its right ascension and its declination. It's going to be very small, but as the stars orbit the galaxy, you're going to see that change. That's what you're referring to here. This is going to tell you about the color, the type of your star, which is your spectral type. So M, K, F, G, A, B, those kinds of things. So of all this stuff on the side here, I'm going to show you how you can go in and change all of that so you don't need all of it, but at least it tells you what it is and what it means. Any questions about that so far? Over here are some of the fun ones. I'm going to take off this grid here. It's just being slow or what? It is. These are all the boundaries of the modern Western constellations, which as you can see can be quite complicated. This computer is incredibly powerful, but it's going really slow because there's so much stuff running at the same time. This shows the illustrations of the figures of those constellations. This shows the names of each of the constellations. No yawning in my class. And this shows the approximate outline trace of the stars that represent their shapes, right? So I'm going to get rid of all that stuff, strip it back down.
Can you edit that?
Sorry?
Is that editable?
Of course it is.
If I wanted to replace it with
yes, we're getting there.
Something else, yeah. Sorry, and question 2.
Yep.
if you wanted to, let's say you were doing a presentation in Melbourne tonight,
Yeah.
and you wanted to say to them, by the way, this is what it looked like 10,000 years ago, 20,000 years
Yes.
ago. That's all possible as
We're
well.
gonna do that next.
Cool.
Yes. So what I'm gonna do is I'm gonna bring the sky back around so the whole sky is in the image. I'm gonna go back, we've got the atmosphere. I'm gonna give this our land as well. So this is what's in the sky. On the left, you have a series of bars, your location window. Where on the earth are you observing from? So this in my system is defaulted to right here in Melbourne right now. So it's gonna have your latitude, longitude, we're assuming we're at sea level, right? System default. I can put in Melbourne or other major cities. North Melbourne's fine. I mean, in terms of astronomy, it's not gonna make, if we put now in Ballarat, the difference is negligible, right? But that's what it means. So if you wanna change it, you can actually click on this to go anywhere in the world. So if I wanna go back to my hometown, go back to mid-Missouri, I just click on that.
It's actually got a different conservation system. It shows different.
We're gonna show the Skylore package in a minute. So I can click on that, that'll change it, but we have to be careful about timing, right?
Yeah.
So how much time do we have right now, actually?
Half an hour.
We got half an hour, we're okay. So if I were to put in St. Louis, Missouri, which is not where I'm from, it was close enough, I spelled it right. The system just doesn't know it. Oh, that's cool.
Maybe faint.
I think it's because of the arrow here.
Right. So if I go to Kansas City, Missouri, and I click on that, all the default stuff is gonna go, the time zones, everything's gonna fall into that. And it all also works on the geographic thing that Missouri is in the middle of the continent, so it's actually 290 meters above sea level, right? Because your elevation is gonna be important as well. We'll just come back down here, we'll come back, see I can put Baldwin North, it doesn't matter, right, it's fine. But when you're doing this, you need to make sure that if you're looking at some place around the world that you've got the appropriate time zone, because that can really throw people off. They'll click on something, they'll think they're there, they're doing their analysis, but the timing doesn't match. The reason is because they didn't make sure the time zone was correct. So you can use a custom time zone, you can enable daylight savings if you want to see what the time or what you're going to see is going to be relative to that time of the year. You know, we use it here. Here is going to be your date and time, so year, month, day, hour, minute, second. So I can just go forward in time by seconds, I can go forward by hours, or even by days, or by years. If you want to really get into it, you can put in your JD, your Julian date, which is this long stream of numbers. If you don't know what that means, don't touch it. Just go back to date and time. This is all you need to worry about. The number one rule is if you don't know what it means, figure it out. Don't start playing with it or it's going to throw everything out. Sky viewing options window. There's a whole lot of stuff in here. Most of this is going to have a default. I wouldn't mess with default, right? Now what I did before is the system has set up, I can put in a limiting magnitude. Now right now, if I want to zoom in to the sky, it'll pull up stars that are super faint as long as I just keep diving in. I can just keep going. It does get to a particular limit. Which means this can be really cool if you want to see something about other stars. So what is Rigel Centaurus commonly known as?
Alpha Centauri.
Alpha Centauri. And what's special about Alpha Centauri?
So the
Close
aliens
star
come
of
from.
the-
Closest star of the solar system. What'd you say?
That's where aliens come from.
Yes, that's the closest star, right?
That's what I was thinking.
And what do we know about Alpha Centauri in terms of
It's really close to us.
really close to us? Thank you, very good. It's exactly, as you can see from it, where's the, I'm trying to find the left side here. It is 4.4 light years away approximately, but we know it's a binary star.
Yes.
In the book, it's a triple star system.
So we go, it's what? We go close enough, we can see it's actually two individual stars, right? We can get details on those. So through a telescope, you'd be able to resolve it as two independent stars. Now, what's really cool about this is if you were to go in and look at, say, the planets. My planet thing is on, so we can see stuff. There's not much in the sky right now, it seems. I'm gonna move forward in time until I can see some bloody planets going up. Where are they?
Morning should be.
Saturn, there we go. Saturn, I'm gonna centralize Saturn. I'm gonna take the atmosphere off just to make it easier for us to see cool stuff on it. We can zoom in. We can see Saturn in extreme detail. It will show you what moons are occulting it or moving behind it. And even if I want to go into some of the individual moons, I can do that. I can zoom into them to a certain limit. But if the reason it does is it can show you where, if you're looking through a telescope, what to look for. And you'll notice over long periods of time, this is kind of cool. Watch this. If I center that, I just think this is cool. This is just a me thing.
Saturn revolving around. It's good.
You can show over time as you're moving in front of and behind it, right? But another cool thing about Saturn is if you look closely and I start skimming through the years, what are you going to notice about it? Oh, hang on. You gotta make sure it's centered.
The rings.
Get rid of the land. The tilt of the rings is going to change.
At the moment, it should be.
Right now,
it should be almost invisible.
Yeah, they're so. Yeah. It's like, well, we're 2025. Hello. What month is it again?
Right.
And the date is
16th.
They're not quite dead on, but we can tell when they are going to be. Right. Oh, we got the closest to that about November. It's going to look at, you're almost not going to see them. They're going to almost disappear. That's just so you can see the cool stuff that it does. I'm getting rid of that, and if I right click on it, it takes it off. Volume max have always got to cause some kind of problem, right?
Just in regards to actually splitting Alpha Centauri in a telescope, should anyone be interested, on Monday at around 7:30, I will be down on South Lawn with a 14-inch Meade doing some observations, looking at Alpha Centauri as one of the objects. So if for some godforsaken reason you're still here at that time, feel free to swing by.
Chance I might be. Yeah.
And what is the sort of like field of view for like naked eye astronomy, like in terms of like degrees on the horizon? Like if we're thinking, oh, okay, if you're sitting looking this way at this year, like how far would you actually be able to see in terms of degrees?
I don't know what you mean.
The horizon.
Along the horizon, like.
What is our FOV? What is the human FOV when
thank you.
applied to stellarium?
Oh, like for ours, well, that's going to vary by person to person. Yeah. So you
like,
can actually go to
the range?
Roughly 100 degrees.
So you can just turn it
roughly it.
Depends on how good your peripheral vision is, but yeah, it's going to be hard to know to start. Well, this brings, I don't want to spend too much time on this, but it's an important one. I remember as a child being in the car with my parents driving, and my mother looking up at a star, and she was actually looking at the Pleiades and saying, that little group of stars, how come when I look directly at it, I can barely see it, but when I look just away from it, it pops out? Yeah. That's something that always stayed with me, and I learned about it when I was older, is because of the photoreceptor cells in the human eye. And I think, raise your hand if you know the answer to that question. Raise your hand if you don't know the answer to that question. All right. So we have two types of photoreceptor cells in the retina of our eyes. There's rods and cones. Cones sense shades of color, and they're centered towards the middle of our retina. Around that are the rods which sense light and dark. It's an evolutionary trait because what happens at night when there's no white light, the cones basically stop working, but the rods are really in full force. It gives us really good peripheral vision at night, which you can imagine in our evolutionary history would have been in high advantage. But what that means is when your eyes adjust to the dark, which takes 10, 15 minutes, depending on the person and the conditions. But if you're out with, no white light around, out far away, deep in the bush, 10 to 15 minutes, within 15 minutes, you're going to have good night vision, which means it's going to be hard to see color unless it's extremely bright. and you're gonna have really good peripheral vision. And what she was talking about is she was getting night vision being in the car. This is a 1978 Lincoln something, like a boat, right? We're in this car looking through, but because her eyes were adjusted, when she looked directly at it, the photons were hitting the cones and barely registering it. But when she looked off a little bit, the peripheral vision was picking up the rods and she could see it much more clearly. So it's a common thing when you're out at night using telescope or, doing a telescope viewing or just looking at the stars, you want to have your night vision. But you'll always notice if you look slightly off the object, it's going to appear better in your eyes. But the second white light hits your eyes, like hitting a reset button, which is why you have the red light. Red light, blue light, green light individually don't really do that. But the white light will do that. Now the red light sort of penetrates deeper, which is why it's a cooler color, which tends to be why whenever you go outside, what we have on the screen here, the red light, that's why you do it. Now, did that answer your question at all?
Yes, thank you.
Anytime you ask me a question, you're going to get the overly complicated, long drawn out answer to that. You're never going to get a simple question.
Correction, by the way, it's actually 200 degrees. That's horizontally and 135 degrees vertically on average.
I was going to say 180 degrees, I can see pretty clearly here.
Yeah,
Go back a bit more than that. Yeah.
Can I ask the basis of your question? Why do you need to know rather than just turning your head to look? Sorry if that seemed obtrusive.
No, that's okay. I was doing for astronomy and world history, we did some observation nights, and when I was trying to compare the use of different instruments to the data from Stellarium, I couldn't work out how far to zoom in as to how far I could actually see.
Okay.
Okay.
So yes, to set the FOV on that to about 200 degrees, and that will be vertically pretty close. You'll have to cut it down a little bit.
So it's 200 horizontally, and then what was it?
135 vertically, according to a thing uploaded to ResearchGate.
Okay.
Good. Something that occurred to me while I was thinking about going.
Too much time. So if you want to limit what stars you see in the sky by their magnitude, you click in this box that says magnitude limit. And you can adjust that by hitting the numbers up or down. Look, it's going to vary depending on the person and the local conditions, whether it's 6. It's usually the order of 6 to 7. Somewhere in that range is the magnitude limit. It's not a hard one, but the closer towards 7 you get, the fewer people are going to be able to see it under the best conditions. What that means is if I set it to 6.5 and I pull this up, it's not going to show me any stars fainter than 6.5. Right.
It will because you've got atmosphere switched off.
It's always something. There we go. So if I zoom in, it's not going to show that beyond. So let's just pick one of the stars we can see in here. It's not showing much of anything. All right. So this one, if I click on it, what's its magnitude? 4.8. So. I wouldn't worry about all these. These are the different projections of how it's going to put in the sky. Just use the default. Don't get too clever with it. SSO, these are solar system objects. Again, I wouldn't worry about this. Not something you're going to have to worry too much about right now. If you click that, it just simply shows no objects in the solar system in the sky at all. When you're doing indigenous astronomy research, this is never going to be the case.
Duane, got a question in the chat from Dwee. I think she's asking if we can put light pollution onto it.
Yes. So there are plugins that do light pollution.
No, I think it's under landscape, or is it?
Light
There
pollution,
is
yeah.
definitely a.
Yeah, there's a scale
It's
there.
there on the left,
Manual
Dwayne.
light pollution. It's on that. Yeah.
Oh,
So
yeah.
under all the 4 check boxes, there's
Light
a.
pollution.
Oh, sorry. Yeah. Oh, yeah. You're right. You're right. Yes. Yes, you can change that.
Yeah, it scales on the orbital class.
Yes, there'll be border scales you can add to that. There'll be stuff for that in there. Yeah. The reality is we could spend an entire semester going through what Stellarium can do. I'm just trying to get us through the basics of it today. DSCO stands for deep sky objects. Again, I wouldn't worry about most of that. That's for the hardcore observers who want to do deep sky astrophotography and stuff like that. For our intents and purposes, don't need to worry about it. Same goes with surveys. Now, before I go into markings, landscape is an easy one. This just tells you like, what do you want the landscape to be if it's during the day? So let's just go move in towards daytime. Put the landscape back up. I can say, well, I want it to be Garching, which is just north of Munich, which is where the European Southern Observatory is. I can imagine it's a hurricane type of environment. Trees, no trees. I prefer to just use zero horizon. What we're doing, that's the best one. Now, there's another thing we can use called horizon, which we're not going to have time to get into at all today. In fact, we might not even have time to get to with what I wanted to today, but we're going to try. Horizon is something we're going to utilize during the cultural astronomy school. It's much higher level stuff, so everybody who goes to that, we're going to learn how to use it there. The two things that are important here are markings and star lore. Star lore I'm bringing in quickly. These are all little packages that have been developed and are being developed for different cultural packages when it comes to constellations and star names, right? So let's pick one. Let's pick the Burong. This goes back and uses the stuff that John Morrison developed. The caveat being that the Burong never said they used connected dots constellations except for a couple of examples. It was obvious for most of the star names that were referring to stars. What John Morrison did is he imagined that all of them were big connected dots constellations and he made them. I don't do that, but if you just look at that as being a representation of what that star is, then it's fine.
Is that the only problem with Morrison? Yeah.
We're not going to get too deep into this or we'll never get anywhere. So if I want to go in to the sky at night, see the names are already in the Regaya language. Kuluk, Guluk, Wapul, Wapul, Wa, in Burmungo, you can see those. Now if I hit the images, it brings up drawings. Now we got a YouTube video that shows how you can create your own images and how you can actually put them into Stellarium and how you can put a whole package into Stellarium. So these are the things that we're wanting to do with each of the communities that we're working with is get local artists to come up with the artworks that represent the object and we can put all this in. There can also be details in the background for all this and what it means. That can all be done.
Sorry, because I'm actually doing that myself. How complex is that? What level of expertise do you need to do it?
Sorry?
I'm just wondering, let's say I had an Indigenous nation who wanted to do this for themselves.
Yes.
What level of Stellarium literacy would you need and how easy it is to drop another artist's image onto that?
It's not difficult.
But it needs expertise.
Well, what you have to realize when you make an artwork, you have to have an idea that it's not going to be projected. It's going to be on a 2D screen, but a
3D
dome background.
Yeah, sure.
Right, so it's going to stretch it as it happens.
Yeah, sure. Okay.
But it shows you have to know where to put the points of the image and how to stretch it so it fits on there just nice.
Yeah, okay.
So you can see how that works in here. And of course, if you just start, I'm just going to move day by day to keep it simple.
Sorry, Duane, you say you have a video of that? Is that, if we just search for that, is the video?
I'll put it online and make sure everybody has access to it. And within this, you can actually click on it. And I mean, again, this tells you the details here, but within the system, when I go inside, all this here is telling you about it. So Burong astronomy tells you about the Burong. You can scroll down, it tells you what the stars and celestial objects mean. That can be as detailed and as thorough as you want it to be.
And Stellarium charge you to upload something or
No.
do you need to get something?
No. Stellarium is completely open access. Now, the latest versions of it, one of the issues with Stellarium is it's been a free package for 20 plus years. They're bleeding money continually.
Yeah, of course.
So they started doing, the recent additions have been, you'll get a basic version of it, but if you want the high-end version, you have to buy it, which isn't very expensive. But that's been the only way they've been able to recoup costs, continue developing it.
Is that for the app or the actual web-based one?
I think it's for the app.
Yeah, you have to pay $25, I think, for that.
It's for the app, but the web-based version I think is still free. I'm not sure things are changing a lot. Now, Stellarium has been really useful because we know the developers. In fact, one of the developers of Stellarium is on the committee for the archaeoastronomy organizations, Georg Zotting in Vienna. anything we needed to do, I've told him, I said, it'd be nice if Stellarium did this. And like a week later, he's like, it's done. I'm like, whoa, wait, what? He's like, yeah. They're doing the most incredible stuff now, using shadow lines and images. So if you want to see what the shadows of the sun are going to look like in this room, you'd be able to do that in Stellarium. It's that wild now. And we're giving a whole seminar on that at the Cultural Astronomy School coming out. But you can do this for a lot of different cultures and things of that nature. Now, where I want to get in, we're going to be running down on time, and I'll have just enough time to probably do one star example in the last 10 minutes, is this. This is where it gets really fun. Now, what does all this stuff mean? Well, let's start talking about it. A lot of these are going to be the J2000 and of date, and we spoke before about what that means. J1950, J2000, every 50 years, there's a full map where you have published what are the coordinates of every celestial object. They're obviously changing over time, and we can measure the change between then and now or then and before, and they're quite accurate. So I can see what the positions of stars and the grids would look like based on the year 2000 or based on the year we're doing it now. So what that means is when you go and you put these stuff in, I almost always use of date because we're moving around in time. We're moving back hundreds, sometimes thousands of years. I want a very accurate representation of what the sky looked like. Now there are the package, the algorithm that's used to measure stellar proper motion and precession. There's a new algorithm that was used that was published in, about 10 years ago. It has an error bar of plus or minus 200,000 years. That means that aspect of it is incredibly accurate. So for example, if I want to go, let me get rid of all this stuff. It's not going to confuse everybody. Here's the stars that would appear tonight at 2:15 in the morning, right? Now, if I want to go back to 2025 BC, I have to put a minus sign in front of that. Right? Considering one important factor, there is no year zero. It goes from the year 1 to the year -1. There is no year zero in Stellarium. Important to remember that. So I can go back. If I go back and put a 1 there, how many years in the past have we gone? If I add this 1 right here, how many?
12,000.
You've gone 1450.
14,000 years ago.
Oh, 14,000.
So this is the year 12,000. This is 10,000 years into the future. All right, this is what the sky will look like. If I go back, this is not by today. This is by year, BC AD or BCE, CE, however you want to define it, right? This is 12,000 BCE, so it's 12,000 plus 2025, so it's 14,025 years ago, right? So you'll be able to notice certain things about stars in the sky that are going to be different from today. So let's just center, for example, Orion. This is what it looked like 14,000 years ago. Oh, it's always something. 14,000 years ago, 2,000 years ago. So I can just really play around with this to see how things change versus now.
So if you plug in 0 into the year field, what numeration of year does that represent? Is that the year 1 or the year -1?
Well, you can put 0 in the year, but it's gonna pull it back by default to year 1.
So if you go in automatically, it goes from 1 to -1, not
well,
1
it'll show 0 if you wanted. Oh no, sorry, that was the thing. It does show a year 0.
Yeah.
I thought it was that it didn't show a year 0. It does show a year 0. Sorry, that is the difference.
So is that 1 AD or 1 BC?
That's
Or
2
this,
BC.
This is 2 BC. All right.
Yes, 2 BC. So I can throw you off if you're looking at things. You have to remember, if you understand you need to understand the parameters of Stellarium and what it does. And I just don't think we're out time to get to the whole point of this was to teach it for the class. We're just not getting to where I wanted to with that. But let's just look right now, 2025. Let's go back to where we were. So I want to get to this point over here. This is your equatorial grid, which we talked about before. This is the same as this button down here. See, equatorial grid. Ecliptic grid shows the path of things with respect to the ecliptic. Azimuthal grid is the one that we're going to use a lot when you're talking about local star calendars. You can look at things like where the equinoxes and the solstices are going to appear at different points in time, because they are going to change slightly with the changes in nutation and the obliquity of the Earth. You've got where the equator is going to be, where the ecliptic is going to be, the ecliptic being the path of the sun in the sky. So that's right here. Which means all the planets are going to be along the ecliptic. Oh, I've got this set to like ancient Egypt or something.
Yeah.
It's always something, right? But you get an idea. They're all going to be along this band in the sky. The meridian we've spoken about, that's an imaginary line that connects north and south through the zenith and nadir. All right, so it goes through the zenith, down to nadir and around. Any star that crosses the meridian, that's going to be when it culminates. If it's circumpolar, that'll be when it upper culminates. If it goes to the bottom, it's the lower culmination. Precession circles is a really cool one. This is if you're doing really deep time stuff. Along this line is going to be where the south celestial pole pointed over time. So you can go back in time and see, where it's going to be. So right now it's up here. Right now it's about here. If you go back far enough in time, about 14,000 years ago, Canopus would have been about 12 angular degrees away from it. Don't worry about all this other stuff. It's going to wind up getting too complicated for everybody. We don't want to get to this because this is mainly in part for my class. What we're going to do right now is just focus on the azimuthal grid and the meridian. Those are the only two things I care about right now. So what we're going to look at is when a star rises or sets, when is it going to heliacally rise or set or chronically rise and set? Let's pick one. Let's say, okay, we're going to go just before sunrise. Now, what were the boundaries? I said the sun needs to be no more than what altitude?
Negative 10 degrees.
Negative 10, right? So let's look at the heliacal rising of an object. And we're kind of using stellarium in a really fun ways. So this line is minus 15, so I want to get that up to where it's about minus 10. I can look over here and I can see it right here, this number. And the object, the star we're looking at, needs to be how many degrees above?
5 degrees.
So incidentally, I can pick the middle star of Orion's belt, fits the exact conditions. This would be considered the minimum heliacal rising of that star. The sun is minus 10, the star is plus 5. There's a 15-degree difference, but it's not any 15 degrees. It's when the sun is minus 10, the star is plus 5. The reality is, how high that star needs to be depends on its magnitude. So the greater the magnitude is, the brighter it is, the lower it can be. Or if it's a second magnitude or a third magnitude, I actually have to be a little bit higher in the sky. But as a first order approximation from what I'm having the first year class do, this works well enough, right? This is fine. This is sort of your earliest time where this is going to be the case. Because as you go on days later, it's going to start rising. The star is going to be higher and higher in the sky. But the minimum date you can see it, sort of the first time, is going to be under these conditions. The same will be if you were to go a chronicle rising. The sun on this side of the sky would still be minus 10 degrees. But we would look back and let's just see what star is there right now that would be plus 5 above the horizon. Well, incidentally, if we look at Gamma Crucis, the top star of the Southern Cross is seen from Melbourne. Well, it doesn't really helically rise because it's circumpolar, but that's kind of what I mean is the idea is that this star gets, as it kind of goes down, it's not going to set below the horizon, but it will kind of start to disappear because the degree of atmosphere it's going through is going to be so great the star is going to be extincted and you're probably not going to see it, at least very well.
Sorry, Duane, just so this is right before dawn, so the star has to be 5 degrees above the horizon for us to be able to see it with the visible, but the sun needs to be 10 degrees below the horizon,
Yeah.
so that it's not
Too bright.
It's not too bright to be able
Yeah,
to see it.
right.
Okay.
Now, again, not only does the altitude of the star in reality depend on its magnitude, but if it's on the opposite side of the sky, it's not going to be as affected by the sun. So it actually depends on its angular distance away from the sun and the sky. This is where there's always more complexity when you get to it. Everything that I present here is always a very simplified version of that. In my classes, it's the same thing. If I were to do a graduate level course on this, which I kind of feel we're pushing towards in this seminar series, but not quite. If I were to develop a graduate level course in this, we'd be deep diving into the real nitty gritty of it and showing all the complexity of it. But the reality is, with the kind of research we're doing, we don't, in very many cases, need that. There's not many cases where we need to dive into that kind of detail. This is just a very good first order approximation because even if we change things out to get into those nitty gritty details, the difference in time is going to be very small. It might not even be more than a day or two. When you're talking about seasonal change, that might be something that occurs over the course of weeks or even a month. It's not going to be something that happens on a specific day. The example of when that might be the case is when you're looking at a lunar calendar, is when can you physically see that first crescent of the moon? Those kinds of things will matter. But when we're talking about indigenous seasonal calendars, even if we applied all of these nitty-gritty details and all this to it, it might not change it by more than a day, if anything. Probably would fall within that day anyway.
Yeah, which basically doesn't matter.
Basically, it doesn't matter. But it's still important to understand the limitations of how it works. So for the students in the class or anybody else who's watching this first order approximation is a very good tool to utilize when we're trying to understand seasonal stars. So whether it's in you might look at when at sunset. Well, the sun has to be at least 10 degrees below the horizon and the object 5 degrees above for those conditions to meet when we say it's going to, helically set. Or for culmination, the sun is 10 degrees when the star crosses the meridian. That's the basic idea of how that stuff works.